Hey everybody, welcome back to Complex Analysis. So today we are going to be talking about other representations of complex numbers. So recall from last time we had two representations. We had the what I called regular old representation x plus iy, and then we had sort of a two-dimensional way of thinking about them, x comma y. Now this may be the algebraist in me, but whenever you have a point, you can also think about it as a vector. So if we have the point x comma y here, all I have to do is connect the origin to that point and boom, we got a vector here. So like we had back in Calc 3 when we had, two-dimensional vectors, we could convert, or we can view this point instead of as in rectangular coordinates like it is now, we can think about it as a polar point. So that's going to allow us to arrive at what we call the polar version of our complex number r comma phi. Okay. And then lastly, we're going to see that trigonometry gives us another way of expressing our regular old number here, and we're going to introduce what's called exponential form. But we'll get into that towards the end of the video. Okay, so let's go ahead and move on. Let's get started. Okay, so again, we can think about our complex numbers if we vectorify them. Okay, as a vector x comma y. Okay, so let's say that's our point x comma y, which I've vectorified. And remember, all this means is it represents the complex number x plus iy. So the x is how long are we going along on the real axis. Remember, the x-axis is our real axis. And then our y-coordinate is telling us how far up the imaginary axis we're going. Okay. Now remember back from Calc 3, we could think about points instead of in what we would call here, again, rectangular coordinates. We can think about them in terms of polar coordinates. So if we construct this right triangle here, so if I drop straight down, okay, the hypotenuse becomes what we would call the length, or our r, okay, and the angle that our vector is making with the positive real axis in this case, we're going to call that phi. So instead of thinking about the point as an x comma y, so you go along the x-axis or the y-axis, we think about it as the polar point r comma phi. Okay. Now what's nice about this interpretation is it still has the same, we still have the same formulas that we did back in Calc 3, which I want to talk about, except we have just slightly different vocabulary for it. So we call r the modulus of z, or the length of z. Modulus of z. But we still have the same formula though. Like we had back in polar coordinates in Calc 3, this is still just the square root of x squared plus y squared. Okay. Then our argument, phi, or the argument is z, or the angle, we call that the argument. Okay, so the argument of z is our angle phi. We call this the argument of phi. Okay. Now you can still use the same formulas that you had back in Calc 3. So x is still equal to r cosine of phi. That's coming from SOHCAHTOA. The ka part of SOHCAHTOA, I should say. Y is equal to r sine of phi. So that's the so of SOHCAHTOA. And then if you combine these, you get that tangent of phi is equal to y over x. Okay. So we still get the same formulas that we did back in polar coordinate land, okay, except now we're just complexifying it. By the way, that's not a word, but in any case, I'd like it to be a word. All right, so let's kind of look at an example here. Let's consider the complex number 1 plus I and 1 minus I. Okay, so 1 plus I, which you can think about as the vector 1 comma 1. And actually, no, not 1 minus I. We change that a little. Actually, no, that's fine. We'll go ahead and do 1 minus I. This is going to be the point 1 comma negative 1. Okay, so 1 plus I will be this vector right here. And then 1 minus I would be this vector here. Okay, So let's go ahead and focus on 1 plus I for a second. So if we want to figure out its modulus and its argument, or an argument I should say, let's go ahead and complete the right triangle. Okay, so we have this leg is 1, this leg will be 1. Then by the Pythagorean theorem, this will be the square root of 2. Okay, and notice we have an isosceles triangle here. Okay, so what angle do we have to have here then? We have to have pi over 4, or 45 degrees. So this point is really just square root 2 pi over 4. And remember, in math, we usually go radians, not degrees. Similarly, if we look at this point, so 1 comma negative 1, we still have a length 1 and 1 here, so this will be square root of 2, but now notice that our angle is rotating clockwise. And so remember, clockwise angles are what we would interpret as negative angles. So this will be, instead of square root 2 pi over 4, this will be square root 2 minus pi over 4. Okay. Now one thing I want to note at this point, notice that modulus is always positive. Okay, modulus is always positive because modulus is the length of your vector. Okay, and there's only one modulus. However, arguments, there's infinitely many for any complex number. Now the reason for this is it's the argument, it's the angle. So let's go ahead and look at our 1 comma 1 there. Use a different color here. So pi over 4 definitely works, right? But we could also go pi over 4 and then rotate another 2 pi, right? That would give us another argument. Or I can rotate twice. Or I could rotate another time. And I can keep playing this game, right? I can keep rotating and get a different argument. Or I could have rotated, by the way, clockwise as well and gotten a similar thing. But in any case, because of the nature of angles, complex numbers actually have infinitely many arguments. Which is actually kind of a funny thing to say, infinitely many arguments. Like they're fighting with each other or something? I don't know. So in any case, just to summarize, modulus is always a positive number. It's the length of your complex number. Okay. Complex numbers have infinitely many arguments just by the nature of angles and rotating by 2 pi. Another note, if you take the absolute value of the difference of two complex numbers, you're just getting the distance between the endpoints of their vector representation. So if we go back here, if I were to look at the absolute value of 1 plus I minus, 1 minus I, okay, notice what are we going to get here? We're going to get the ones cancel out. You get 2i, and then you'll get 2 from that. Okay, and if you notice, if you just take the distance between the tips of their vectors here, okay, what do you also get? You get 2. Okay, so again, if you ever take the modulus or the length of the difference of two vectors, all you're getting is the distance between those vectors, or the distance between the tips of those vectors, or the ends of those vectors. So same thing that we had back in Calc 3. All right. Now, if you guys remember back when we defined multiplication in the last video, we really had that kind of strange multiplication, right? So if I multiplied two complex numbers, we got sort of that weird FOIL, right? We got xa minus yb, comma xb plus ya. Okay. And again, there was no rhyme or reason for doing that, although I did explain towards the end of the last video that if you think about our regular old normal representation of complex numbers, and if you just FOIL, you'll see that these are going to be your real and imaginary parts respectively. But it was still kind of strange, right? Well, if we think about complex numbers in terms of modulus and arguments, we actually get something really cool happening. Okay? So let's investigate that. I'm taking this straight from the book, but I'm going to explain it step by step because your book, I think, just sort of throws it on the page. So let z1 be a complex number with modulus r1 and phi1, and let z2 be x2 plus iy2 with modulus r2 and argument phi2. Okay. So keep in mind, remember, x is equal to r cosine of phi, and y is equal to r sine of phi. Okay, we're going to use that in a second. So now if we just multiply these numbers straight up, Okay, what do we get? Well, we get this, right? And then now if we use our polar coordinate conversions, by substituting, we'll get x1 is equal to this, x2 is equal to this, and so on and so forth for our y's. Okay, so this is using our polar equations. And then the next line, this is from FOIL. Okay. And then the next line is just a little bit of rearranging. And then finally, to get this last line, we use the sum formula for sine and cosine, which may be something you remember back from trig. If not, no worries. But anyway, it's the sum formula for sine and cosine. Now, by the way, I realize I did go through that really fast. What I recommend you all doing, just as a good exercise, you should do this on your own to make sure you're getting the same thing. But I didn't want to make a 45-minute video on doing that. But in any case, what's the point of this? I want you guys to see what happens. When we multiplied these two complex numbers, what did we get in the end? We got r1, r2 times cosine of phi1 plus phi2 plus I sine of phi1 plus phi2. Okay? So what's happening? So if you multiply two complex numbers, really what's happening geometrically is you're multiplying their lengths together. So actually, let me write this. When you multiply two complex numbers, okay, all you're really doing is multiplying their lengths, and two, you're adding their arguments. Okay, so again, just to summarize, when we're multiplying two complex numbers, notice, what did we get at the end of our calculation here? We got r1 times r2, which means that all you did is we multiplied our lengths together. And then inside cosine and sine, notice we got phi1 plus phi2, which just means that we added their arguments. So this is a way of giving you a geometrical interpretation of what happens with multiplication. Basically, if you multiply two complex numbers, you just consider the complex number where you've multiplied the lengths and added their arguments, and boom, you're good to go. Okay? Rather than, again, remember we had this strange multiplication, which is a little bit harder to see, like, why does that actually work? But when you think about it in terms of modulus and argument, it actually gives you a really, really cool and awesome way of thinking about multiplication. Now, one thing I want to point out here, which maybe is no surprise, notice that cosine and I sine were sort of apparent in this calculation, or they were there in the calculation a lot. And actually, this expression, cosine of phi plus I sine of phi, appears a lot in complex analysis. And so we actually give it a special name, e to the I phi. Okay, so cosine of phi plus I sine of phi, we're going to denote that by e to the I phi. Now, when you look at this, you might be like, it's an exponential function? Where the heck did that come from? So I just want to put a little note here. Note, this is notational. This is purely notational. This is purely notational at this point. Meaning the reason why we're calling it e to the I phi is only because we're trying to be a little bit more efficient. Mathematicians don't like writing cosine of phi plus I sine of phi over and over and over again, right? So instead of writing this whole expression out, we're just going to call this e to the I phi. We will talk about a complex exponential function at some point, but that's not today though. Okay, but in any case, we are using exponential notation, but it's not an exponential function or anything like that. Okay, we'll get to that later. However, the reason why we are using e though, or this exponential notation, it does have similar properties that our exponential functions had back in, pre-calculus and calculus. So let's go over that a little bit. So part A here is saying sort of what we expect. If you multiply two exponentials, what do? You add their exponents. Okay, which is, again, that's a property that we use all the time in calculus, right? B says if you take e to the I 0, you get the number 1. Again, very similar to what we had back in calculus. Part C here says if you take 1 over e to the I phi, you can rewrite it by putting a negative sign in your exponent. Again, similar to what we had back in exponential functions. Now, something that's not similar is this right here. So e to the I phi plus 2 pi is actually just equal to e to the I phi. Okay, now where that's coming from is it's coming from angles again. If you take phi and you rotate that another 2 pi, you end up at the same place, right? Okay, so that's where that property is coming from. But this is something that's very different from what we had back in calculus, right? That's not true for regular old e to the x. E to the x is not e to the x plus 2 pi. Okay, so kind of cool, right? We have this exponential notation. It's acting similarly, but yet in some ways it acts very differently. Part E here says if you take the length of e to the I phi, you just get the number 1. So it has unit length. And then F here, this is something that's similar to calculus as well. If you take the derivative of e to the I phi with respect to phi, you get I e to the I phi. Okay? And that I is coming from the chain rule. Okay. So in any case, this notation, we did use this notation very, how should I say it? We're using it with intentions. There's a reason why we're using the exponential notation. It's because it has similar properties. It's not exactly the same as we see in part D here, but it acts very similarly to the exponential function. Okay. Roots of unity. So the proposition, let me go back. The proposition parts B and D in particular tell us that, or gives us a way of solving certain types of polynomials. So if you're considering the polynomial z to the n minus 1, or solving the equation z to the n minus 1 equals 0, notice that our properties imply the following. Okay, so if you take e to the 2 pi im over n and you raise that to the nth power, you're going to get the number 1. That means that if we were to substitute this number inside this equation, we actually get a root. Okay, so in fact, e to the 2 pi iq, where q is some rational number, actually gives you a lot of power when you're trying to solve these equations. So we give them a special name. We call them roots of unity. So a root of unity is just a complex number of the form e to the 2 pi iq. Okay, now we usually, again, mathematicians being efficient, we usually don't want to write e to the 2 pi iq, so usually we use, it's always hard for me to write, we use the Greek letter zeta to denote this exponential here. Okay. Now if zeta to the n is the smallest n, then we call zeta here the primitive root of unity. Now if you go into not complex analysis, if you go into number theory, usually what happens, or at least my experience with roots of unity, you can sort of generate the other roots of unity using the primitive root of unity. So that's why we sort of call it out a little bit and give it a special name. In any case, an example, the fourth roots of unity are plus or minus 1 and plus or minus I. So this means that they are the solutions to z to the fourth minus 1 equals 0. And I recommend everyone plug those in, make sure you do get 0. It is true. Okay, but in any case, there's examples of roots of unity there. Okay, so we're going to end the video today with our last presentation of complex numbers. So remember, we called cosine of phi plus I sine of phi. We had a special notation for that. That's e to the I phi. That's our exponential notation. So if we take x plus iy, which is our complex number, and we use our polar equations, we'll get r cosine of phi plus I sine of phi. Whoops, and I forgot an r here. I don't like how I wrote that. One second. There we go. I r sine of phi. Okay, so using our polar equations for x and y. Okay, and now if I factor out r, we're going to get r cosine of phi plus I sine of phi, which using our new exponential notation, this is just r e to the I phi. Okay, so here's our last representation of a complex number. We can think about any complex number as r e to the I phi, where r is the modulus or the length, and phi is some argument. Okay, and we call this exponential form because Spoiler, it's an exponential, or it looks like it's an exponential. So just to summarize, we do have, these are our ways of thinking about complex numbers. I'm a little bit of a stickler. I usually associate these two as the same thing because I think about points as vectors. Maybe that's the algebraist in me, so I really think we have 4, but your book actually says that it's 5, which, okay. In any case, so we have our two-dimensional version of thinking about them, okay, either as a vector or a point. We have polar coordinates, which we just talked about. Again, that's coming from Calc 3. And then we can think about our complex numbers in rectangular form or regular old number form, or also exponential form here as well, r e to the I phi. Now notice here your book, a little bit inconsistent here. They're using theta there, so just keep in mind we're going to be using either theta or phi in your book just to denote the argument, so just bear with us with that. But in any case. All right, everyone, that's it for this video. I will see you all next time.